Hi guys, I go by the name of Kamrelo. I'm widely known as King K and Harry. In today's revision class for Physics 171, we will be looking into fluid mechanics. Fluid mechanics is one of the fundamental branches of physics and engineering that deals with the behavior of fluids and the force that is applied on them. Fluids can be classified as liquids, gases, and can also be classified as plasma when exposed to higher temperatures. Fluid mechanics, it consists of two branches, the statics, which deals with bodies at rest, and the dynamics, which deals with bodies in motion. So by definition, basically, fluid mechanics deals with the behavior of fluids at rest or in motion and their interaction with solids. There are several terminologies that you have to familiarize yourself with in fluid mechanics, and it is important for you as a student that you understand them properly, as they are crucial in solving many physics problems that arises in fluid mechanics. We have the density, the first terminology. Density, which is represented by the symbol rho and is defined as materials mass per unit volume. We also have the fluid pressure. As we are all aware that a fluid is a substance that can flow or be classified as a liquid or gas, even plasma when exposed to higher temperatures. So fluids are those type of substances that cannot resist shearing stress. Unlike solids, solids can withstand the shearing stress. Shearing stress is a type of stress that occurs when a force is applied parallel, tangential, or perpendicular to a surface, which causes that material to deform if it's a solid or to flow along a plane when it's a liquid. And this shearing stress is represented by the symbol tau, and mathematically is defined as the applied force divided by the cross-sectional area. So that is the shearing stress. So any material that can resist the shearing stress is known as a solid. And under the influence of a shearing stress, it's gonna deform. But as for liquids, under the influence of a shearing stress, what happens to solids, to liquids, is that they, not specifically liquids, but fluids, under the influence of shearing stress, they deform continuously. They deform continuously, and this force is described in terms of pressure. So the pressure, the fluid pressure, is given by the applied force divided by what? By the cross-sectional area. We also have the gauge pressure. The gauge pressure is the difference between the actual pressure, which is also known as the absolute pressure at a point, and the atmospheric pressure. Mathematically, the P gauge, which is the gauge pressure, and then it's equals to the P absolute, which is our actual pressure, minus the P atmospheric pressure. That is the other type of pressure that you have to familiarize yourself with, because in some questions you will be required to find the P gauge, or in some instances, you will be given the P gauge and you have to solve for other unknowns on the question. And in such cases, you are forced to actually find first your absolute pressure, which is the actual pressure at that point, and therefore you can then use that pressure to solve for what is required in that question. Okay, now we look further now into pressure variation with height and depth. So when we look further into this, you have to familiarize yourself with the Pascal principle, which states that the pressure applied to an enclosed fluid will be transmitted without a change in magnitude to every point of the fluid and to the walls of the container. That is the Pascal principles. And you also have to know the Archimedes principle, which states that FD is equals to MF multiplied by M sub F. This is M sub F multiplied by G, where your F of B is the buoyant force, is the buoyant force that comes from the surrounding fluid, and it's basically acting on that body. So that this buoyant force is given by the mass of the fluid and then multiplied by G. And then we are now looking into the ideal fluids. Okay, so ideal fluids have their own characteristic. So we're gonna look into the following characteristics, and any fluid that have these characteristics can be classified as an ideal fluid. For you as a student who is studying physics and is doing fluid mechanics, it's important for you that you understand these characteristics as they are crucial in solving many problems in fluid mechanics. So these characteristics are mostly your assumptions, as you need to state your assumptions before you can actually solve problems. So for ideal gases, we're gonna look into those characteristics. For ideal gases, the not ideal gases, I'm sorry, ideal fluids. Okay, so let's look into that. So in order for you to classify a fluid as an ideal, firstly, the fluid needs to be incompressible. The fluid needs to be incompressible. Incompressible meaning there is no change in density. And then secondly, an ideal fluid lacks viscosity. Lacks viscosity. So viscosity refers to the thickness of the fluid. I can use a honey as an example. Okay, a honey has more viscosity than water. Okay, because when you can pour a honey on a table and water, like the honey will move at a slower velocity, at a slower speed, unlike what? Unlike water. Therefore, a a a a a a, a material that has a higher viscosity, it's less likely to classify that type of fluid as an ideal fluid. Okay, so in most cases, we for fluids that have more viscosity, we say that they undergo a viscous flow, a flow in which the frictional effects are more dominant or are significant. But for those that lacks viscosity, we don't necessarily mean that their viscosity is zero, because by definition, each and every fluid has its own viscosity. So when we say lacks viscosity, we simply mean its viscosity is negligibly small. Okay, it's negligibly uh, small. So this occurs mostly in inviscid flow regions where the viscous forces are negligibly small compared to the initial or the pressure force in acting on that fluid. Okay, so that is the second characteristic. And then the third characteristic is that the flow needs to be steady. Okay, the flow needs to be steady in order to classify that fluid as an ideal fluid. So steady means that there is no change at a point in time. And lastly, the fluid flow needs to be irrotational. To be irrotational. And then we move, and then we're gonna look into the fluid patterns. So yes, guys, these are the characteristics that you have to familiarize yourself with under fluid mechanics in order for you to classify a fluid as being an ideal. It needs to be incompressible, it needs to lack viscosity, and then have a steady flow and be rotational. So these are very important characteristics that you have to make sure that you understand fully, people, because in some questions, you'll have to make assumptions. And these are mostly assumptions that you make, that my fluid is incompressible. There is no any change in density. Therefore, the density at point A is equal to the density at point B. So basically, these assumptions will help you reduce your equation into a simpler form and then eliminate some of the terms that are in there in order for you to solve for what is required. Okay, so now, like I said, we are now moving, and then we are looking into the fluid patterns. So specifically for for physics 171, I think you are mostly focused on streamlines. Okay, we also have the path lines and the streak lines, but I'll just touch on the streamlines. So a streamline, it's in simple terms, it's is the path followed by an individual fluid, is the path followed by an individual fluid, and then mathematically we can say it's a line that is everywhere tangent to the velocity field. So if you have your Cartesian plane, this is your y, your x, and this is your function. So a line that is tangential, let me use a different color. A line that is tangential, that is everywhere tangent to the velocity field. that will be the streamline. So we're gonna have this, and then we know that obviously this will be a 90 degrees angle, and then you have your velocity fold along the y-axis, and then you have your velocity fold along the x-axis. Okay, so by definition, your change in y over the change in x, it's equals to v over u. Therefore, u dy will be equals to v dx, which is equals to 0. And this is the fundamental equation you can use to find the equation of your streamline, which is the path followed or taken by an individual fluid. Okay, so in a more generalized or compact form, we can say that dx over u is equals to dy over v, it's equals to dz over w. Okay, because your velocity can also be given as a function of u, v, and w, not just as a function of u and w, and can also be as a function of v and w, or u and w. So it depends on the type of question that is given. So this is the equation that you use to find the equation of your streamlines. And then now you have to also know what we call the continuity equation. So any flow within a tube, it obeys what we call the equation of continuity. And according to the equation of continuity, the volume flow rate, which is represented by the letter R sub V, it's equals to the cross-sectional area at that point multiplied by the speed of the fluid at that point. Okay, and it also obeys the mass flow rate that states that, which is represented by the letter Rm. The mass flow rate is equals to what? To rho, which is your density multiplied by the volume flow rate. And this is equals to a constant. Okay. Even here, it's equals to a constant. This is also equals to a constant. Okay. And then lastly, as part of the summary, you have to also know how to apply. There's a very useful equation. It's a very powerful equation that is going to help you solve as many problems as you can in fluid mechanics, and it's known as the Bernoulli equation. It's known as the Bernoulli. It's known as the Bernoulli's equation. So Bernoulli's equation stems from the principle of conservation of mechanical energy, which is applied to the flows on an ideal fluid. Okay, and then so mathematically it is given by pressure plus half density velocity squared plus p, then g multiplied by y, which is then equals to a constant, where y is the elevation. In simple terms, we mean the height, right? And this is your density, and this is your pressure. Okay, so it's a very useful equation. It's a very useful equation that you're gonna be using to solve problems in fluid mechanics. So let me say in a practical sense that you are given a system, and then you have to find the pressure. You are given a system, and it consists of two sessions, session 1 and 2, and you have to find the pressure at session 2. So you can make use of the Bernoulli equation, because according to Bernoulli equation, under the context of the principle of conservation of mechanical energy, the pressure at session 1 plus half rho by the velocity at session 1 squared plus P at session 1, and then G by the Y at session 1. It's equals to the pressure at session 2, and then plus half, and then by rho, and then V2 squared, and then plus P at 2G, and then Y2. Okay. So this is how useful Bernoulli equation is. And then from your assumptions, you can be able to eliminate some of the terms here. Okay, let me say they say that the flow flows horizontally. If the flow flows horizontally, there is no any change in height. Therefore, the influence of elevation is negligible. Okay, as a result, your y is a 0. And in that case, you already see that you have eliminated this term, which is the PGY1 and then P2GY2, right? And you are only left with P1 plus half PV1 squared is equals to P2 plus half PV2, right? And then with this information, then you might be given V1, and you have your density, and you have P1 and P2, and then you can solve for V2. So you have to understand this equation and know how to apply it. Mostly this equation, when you apply it, you need to state some certain assumptions based on the question that is given, and then you will be able to solve for what is required. Okay, so that is the some important summary that I wanted to share with you before we can actually move into questions. Okay, I hope you find it very helpful.